Okay, now we move to talk about a new chapter about continuous probability distribution. We already talked about discrete probability distribution, and if you remember, we said discrete random variable can assume clearly separated values such as 0, 1, or 2, or 3. Okay, this is the meaning of a discrete random variable. However, now we talk about continuous probability distribution, which usually results from measuring something, okay, such as the weight of a travel luggage. This weight could be, for instance, 10.6 kilogram or 25.8 kilogram, and so on and so forth. The distance a student walks from home to school could be 1.2 kilometer or 2.5 kilometer or 2 kilometer, okay? This is a continuous, of course, random variable. For a continuous distribution, we may wish to know the percent of observations that occur within a certain range. Let's give you an example here. Let's say we select 4 individuals, okay, and find their weights, and say their weights are, let's say, 50.6 kilogram, 60.7 kilogram, 78.2 kilogram, and let's say 80.5 kilogram. So these are continuous, values, okay? Now we may say, what is the percent of individuals who have weight less than 70 kilogram? What is the percent of individuals in those 4 individuals? We may wish to know the percent of individuals who have weights less than, let's say, 70 kilogram. We say, well, though the individuals who have weights less than 70 kilogram, we have the percent of individuals who have weight less than 70 kilogram. We have 2 here. So we have here 50% of the individuals have weight less than 70 kilogram, okay? It's important to realize that a continuous random variable has an infinite number of values within a certain range. For instance, a recorded time of 0.53 seconds could mean any measure from 0.525 up to 0.535, but not including 0.535. Okay, 0.525. It's, if you round it, becomes 0.53. Okay, any number from here all the way to 0.535, but not including 0.535. So you have a bunch of numbers within this range, and infinite numbers of values within this range. So this is basically what we're talking about when we say a continuous random variable. Now, here we're going to talk about the families of continuous distribution. When we talked about discrete random variable, we said we have a binomial distribution. Is a distribution that is based upon discrete random variables. Now, here an example of a continuous distribution is we're talking about the uniform probability distribution. So the uniform probability distribution is an example, or is based upon continuous variables. What is a uniform probability distribution? Is rectangular in shape and is defined by minimum and maximum values. Okay, let's give an example here that illustrates a uniform probability distribution. let's say the time it takes a bus to travel from Beirut, Lebanon, to Amman, Jordan, ranges from 5 hours to 8 hours. Here, the random variable is the travel time within this range or this interval from 5 to 8. So what's the random variable here? The random variable is the travel time. This random variable is continuous in the interval from 5 hours to 8 hours. Why? We have a range. We have minimum value 5 hours, maximum value 8. But it could be any time between 5 and 8. It could take the bus 5.1 hours, or 5.2 hours, or 5.3 hours, and so on and so forth. It could take the bus 7.1 hours, 7.2 hours, 7.8 hours. So you have an infinite number of values that the bus will take to travel from Beirut, Lebanon to Amman, Jordan. So this is an example of a continuous random variable, and it illustrates the uniform probability distribution. Okay, now, of course, we go further to discuss some properties of the uniform distribution. The shape of a continuous uniform distribution, as you can see, the shape is rectangular. Okay, the example that I gave for a bus traveling from Beirut to Amman, it takes between 5 hours to 8 hours. If I want to draw the uniform distribution of this example, I will come up with this type of distribution. This is the minimum time, this is the maximum time. So, and then the probability of it is 1 over b minus a. Okay, this is the probability of the uniform distribution is given by 1 over b minus a. Okay, so I put along the vertical axis the probability. So it is 1 over b minus a, 1 over 8 minus 5. We'll get 1/3, 0.33. And then this is the height of this rectangular figure, okay, which is the uniform distribution. And the length of it, okay, or the base of it is 8 minus 5. So 8 minus 5 will get, of course, 3. Of course, this is the base, and the height is the probability of it. So this will give you the rectangular shape of the uniform distribution. Now, therefore, the mean or the shape of the continuous uniform distribution is, as you can see, is rectangular. Okay, it has a base and it has a height. The height is the probability, and the base is the difference between the maximum and minimum. 8 is the maximum, and minimum 5. 8 minus 5. So the mean of the uniform distribution is, of course, the average, a plus b over 2, which is the average of the mean and the maximum values. So this is the mean of the uniform distribution. Mu is equal to a plus b over 2. The standard deviation is the positive square root of the variance, which is the square root of b minus a squared over 12. Okay? The equation of the uniform probability is given. The equation of the uniform probability distribution is P of x is equal to 1 over b minus a. Okay? If x between a and b in this closed interval, a and b, and it's going to be equal 0 outside, this interval. So the probability is 0 if it is outside the interval between the minimum and the maximum value. Area of the uniform distribution is 1 over b minus a times b minus a. Just the one that I just explained here. So 1 over b minus a, of course, it is the probability of the uniform distribution, which is along the vertical axis. Okay, the probability here in this example is 1/3. Okay, times the base. The base is the maximum minus the minimum. Maximum minus the minimum. So 3 times 1/3, you will come up with the area of the uniform distribution in that problem or in that example. Now, let's give an example about the uniform probability distribution. Say that we have a uniform distribution that is defined over the interval from 5 to 15. Okay? You have some questions regarding this example. The first question is draw a graph of this distribution. Okay? This is the graph. This is solution here. Okay? A, draw a graph of this distribution. Of course, similar to this one over here. Of course, the base is, you have the minimum value 5, the maximum value is 15. So we do, this is the base, and the height of it is the probability, which is 1 over 10, or 0.1. This is the graph of the distribution. B, what are the values for A and B? The values A equal 5, and B equal 15. These are the values for A and B. C, what is the mean and the standard deviation of this distribution? The mean is here, the standard deviation is here. These are the formulas for the mean and the standard deviation. Of course, the mean is mu is equal to A plus B over 2, 15 plus 5 plus 15 over 2, you come up with 20 over 2, you get 10. So the mean is 10. What about the standard deviation? The standard deviation sigma is going to be equal square root of, this is over here, B minus A squared, 15 minus 5 square into square, of course, over 12, 10 square over 12, 100 over 12, you come up with 2.89. 2.89, this is the standard deviation of this uniform distribution. What is the area D? What is the area of this distribution? Of course, the area is base times height. This is the base, 15 minus 5, times the height, which is 1 over 10 or 0.1. So 15 minus 5 times 0.1, we come up with 1. So the area is 1. The area is 1. Now, part E says find the probability of a value more than 10. So we need to find the probability of this distribution when a value is more than 10. Okay? Remember that the area within the distribution for the interval 10 to 15, the area more than 10, but it's going to be less than 15, from 10 to 15. So find the area, the probability of a value more than 10. We start from, we get the interval from 10 to 15. Therefore, the area within the distribution for the interval 10 to 15 will represent the probability of a value more than 10. Okay? So the probability more than 10 is basically the area between 10 and 15, between 10 and the maximum value of the interval, which is 15. So probability of x between 10 and 15 is going to be the base times the height. Remember here, the height is the same. The height, no change in the height, because the height is the probability, which is 1 over 10. Okay, however, the base will change because we're talking about from 10 to 15. Now, the base is going to be 15 minus 10 times 0.1, and we come up with 0.5. Okay, we come up with 0.5. This is the probability, okay, of a value more than 10. Now, what about part F? Find the probability of a value between 6 and 10. Between 6 and 10. Okay? The probability between 6, x between 6 and 10, of course, remember the height, no change in the height, which is the probability, no change in the height, which is 1 over 10. However, the base now will change between 10 and 6, which is difference is 4. So we get 0.1, the height, times the base. Okay, we could say here, okay, the base 10 minus 6 times the height times what the height, which is what? 0.1, which is 4 times 0.1, which is, of course, 0.4. This is the probability of a value between 6 and 10. Okay, now we talk about the normal probability distribution. Its equation is given by this formula over here. P of x is equal 1 over, sigma times radical 2 pi, of course, multiplied by exponential e, the base of the natural log e, into minus x minus mu square over 2 pi square. This is a complex formula. Of course, we are not going to be, concerned about it in terms of the calculation of the probabilities. However, it is a formula of the normal distribution. X is the value of a continuous random variable. Of course, the pi is a mathematical constant, which is equal to 3.4. E also is a mathematical constant, which is the base of the natural log exponential, which is equal to 2.718. Mu and sigma refer to the mean and standard deviation, of course. And as you can see, that the normal distribution is defined by its mean, mu, and its standard deviation, sigma. Now, as I said, the normal distribution is defined by its mean, mu, and standard deviation, sigma. There is no need, of course, for the normal distribution equation, the one stated over here, to make any calculations. Of course, we're going to use only the table to calculate the various probabilities. Okay, no need for the equation or the formula of the normal distribution to make any calculations of various probabilities. Instead, of course, we'll be using table to look up all the various probabilities that you will see later on. Let's look at the characteristics of the normal probability distribution. Of course, the normal distribution consists of the following characteristics. The first one, as you see, it is a bell-shaped and has a single peak. This is a normal distribution. It has a single peak over here, okay? At the center of the distribution. This is the center of the distribution, okay? At the center you have the mean equal median equal mode, okay? It's clear? So it is, it is bell-shaped, as you can see. The mean and median and mode are equal at the center of the normal distribution, okay? And they are located at the center of the distribution. The second characteristics of the normal distribution is that it is symmetrical about the mean. You have two halves, and these halves are equal. And the area to the left of, under the normal distribution, to the left of the mean is equal 0.5. Okay, here it is 0.5. And here also it is 0.5. So the area under the curve to the left of the mean is 0.5, and the area under the curve to the right of the mean is also 0.5. Why? Therefore, because these two halves are symmetrical, they are equal. They are mirror images of each other about the center or the location of the about the center of the distribution. The third characteristic is that it falls off smoothly in either direction from the central value. Okay, that is, the distribution is asymptotic. This means that the curve gets closer and closer to the x-axis, but never actually touches it. As you can see, the tail. This is the tail of the normal distribution, and this is the tail. Here, the tail to the right, and here the tail to the left. As you can see, those, it gets closer to the x-axis, but never actually touches the x-axis. Okay, it's called asymptotic. Asymptotic, it's very close to the x-axis, however, it doesn't touch the x-axis. Okay? And the fourth characteristic is that the location of the normal distribution is determined by the mean. Okay? The location of the normal distribution is determined by the mean. Now, this graph actually resembles or represents all these characteristics of the normal distribution. As you see, the two halves of the normal distributions are symmetrical. This half from the central value is equal to this half. These two halves are symmetrical, so the area under the curve to the right of the mean is equal 0.5 and is equal to the area under the curve to the left of the mean, which is equal to 0.5. Okay? With a continuous probability distribution, areas below the curve define probabilities. So the areas below the curve, as we will see in later, will define probabilities. And remember that the total area under the normal distribution, under the normal curve, is equal to 1. 0.5 plus 0.5 equal 1. And the area to the under the curve to the right of the mean is 0.5. The area under the curve to the left of the mean is also 0.5 with a total area of 1. Okay. Now, as you can see here, the number of normal distributions is infinite. We have unlimited number of normal distributions, each having a different mean, standard deviations, or both. So you're going to have an infinite number of normal distributions, each having a different mean, a different standard deviation, or both. Therefore, providing tables to find probabilities for the unlimited number of normal distribution is almost impossible. Therefore, what happens? One member of the family of normal distribution can be used to find the probabilities for all normal probability distributions. It is called the standard normal probability distribution. So, because it is impossible to calculate probabilities or to have tables to find probabilities for any normal distribution, because we have an infinite number of normal distributions. So fortunately, there is one family of the normal distribution that can be used to find or locate or calculate the probabilities, which is the standard normal distribution. Okay. The characteristic of this standard normal distribution is that it is unique. It has a mean of 0 and a standard deviation of 1. Okay, so in order to calculate the probabilities of any normal distribution, so what we do, we convert this normal distribution into a standard normal distribution that has a mean of 0 and a standard deviation of 1. Okay? Now, any normal distribution can be converted into a standard normal distribution by subtracting the mean from each observation and dividing the difference by the standard deviation. The result are called z-scores or z-values. Okay? Now, the z-score now is equal x minus mu over sigma. So any normal distribution, in order to calculate the probabilities, what we do, we transform it or convert it into a standard normal by using this formula, by using the z-score, which is equal x minus mu over the standard deviation. Once we do that, then the z-score will have the same characteristics of the normal distribution, okay? And we have a table for the standard normal, okay? So once the normally distributed observations are standardized, the z-values are normal distributed with a mean of 0 and a standard deviation of 1. So the z-score is normal distributed with a mean of 0 and a standard deviation of 1. Okay? Therefore, the z-distribution has all the characteristics of any normal probability distribution. So, to conclude, we say that because we have unlimited number of normal distributions, then it's impossible to have a single table to calculate the probabilities. So what we do, we can convert any normal distribution into a standard normal distribution with a mean of 0 and a standard deviation of 1. And we have tables for standard normal. So once we do that, we can locate the probabilities of any normal distribution.